continuing our discussion about the physiology of the kidneys, we look at the vascular resistance in microcirculation, because we know that the kidneys have the renal arteries coming directly off of the aorta, which means you've got to somehow get that high pressure aorta down into the kidney glomerulus without destroying it. So what ends up happening is we're dropping the pressure from about 95 millimeters of mercury when it comes in down to about 8 millimeters of mercury by the time it hits the actual glomerulus. Now, that's kind of impressive. That's a very fast drop in a very short distance. But while the glomerulus still has higher pressure than a lot of other capillaries, it still has to be lower than most other blood vessels. The key thing here is the resistance in the afferent arterioles. Because arterioles are a high resistance vessel, they help to also buffer the actual blood pressure and the actual amount inside the glomerulus. Because you need to maintain a pretty consistent pressure on the glomerulus to keep the filtration occurring. If that pressure in the glomerulus drops too much, the filtration process starts to slow down. You don't get as much filtration occurring. So you somehow have to buffer that to make sure you maintain enough pressure, even though your blood pressure might fluctuate. Your blood pressure might go up because you're exercising. Blood pressure might go down because you're resting. So all those fluctuations have to be pretty much leveled out by this afferent arteriole. And the resistance that it has helps it keep a consistent pressure inside the glomerulus. So one other thing that's interesting about this, and we start looking at the filtration and movement, is this Juxtaglomerular Apparatus, or JGA. Now the Juxtaglomerular Apparatus are these cells right here. You'll notice that this is the afferent arteriole coming in. So afferent arteriole goes in, and that's where you have the JGA cells, the Juxtaglomerular Apparatus cells. Now I'll get to those in 1 second, one other thing to focus on. In green here, that's the macula densa cells. You'll notice the macula densa cells are in the distal convoluted tubule. So you have this afferent and then efferent arterioles coming in and out. So that's the renal corpuscle. And the distal convoluted tubule is right next to it. That, an anatomical idea here means they're going to interact. These macula densa cells have chemoreceptors for sodium, Cl. It's not the only thing they measure. They also measure other things, but that's one of the key things they're measuring. So therefore, if the macula densa cells register sodium chloride salt dropping, so levels are not where they should be, they're below homeostasis, they can trigger the juxtaglomerular apparatus, the JGA cells, to then act, basically cause a response. So that's what we need to look at, is how this whole setup, how this whole system is working together. Which brings us to this. Now there's a lot on this slide, so I'm going to blow it up full screen. So what you're seeing here now is, we're going to start with, again, that JGA, the Juxtaglomerular Apparatus. The JGA, so let's say the macula densa cells don't register enough sodium, so those chemoreceptors say, hey, there's not as much sodium as there should be. Or there's a low fluid flow, so you have a decrease in blood flow. Or a decrease, I should say, in fluid flow. This is the filtrate, not the blood, sorry. So a low amount of fluid flowing through here. What'll happen is these macula densa cells are going to cause the actual JGA cells, the juxtaglomerular apparatus cells, to release renin. Now, that release of renin from the kidneys is going to go right into the bloodstream. In the bloodstream, the enzyme renin now is going to come into contact with angiotensinogen, which is released from the liver. Now, angiotensinogen is not active yet. Renin will activate it. It'll end up becoming angiotensin 1. Now, angiotensin 1 will keep circulating the blood, but once it gets into the pulmonary circulation, so around your lungs, you're going to have an ACE enzyme, or known as an angiotensin converting enzyme. is going to convert angiotensin 1 into angiotensin 2. Now, angiotensin 2 is going to be quite important because it does a couple different things. Angiotensin 2 can do one thing, that's this upshoot here. It'll trigger vasoconstriction. If you vasoconstrict, you're going to increase blood pressure because you're taking that getting smaller. Increasing blood pressure means you send more blood into the kidneys for more filtrate. That would increase the amount of fluid inside the actual macula densa cells they're reading. Secondly, the angiotensin 2 will also stimulate the adrenal cortex. So now we're going back to the endocrine. By stimulating the adrenal cortex, we're producing aldosterone. Now, hopefully, if you think back to endocrine a little bit, aldosterone can do a couple different things. One of the big things that aldosterone does, though, is aldosterone deals with sodium levels. That means aldosterone is going to stimulate the kidneys to reabsorb more sodium, pull more sodium back into the blood. So that's going to help increase the sodium levels that were low, that originally the macula densa cells picked up on. But also, we can then trigger through ADH, causing the aquaporins to help with collecting more water. So again, we're having multiple different things all helping here. We're looking at the combination of vasoconstriction, looking at the adrenal cortex, aldosterone, looking at ADH and aquaporins, more fluid back. But overall, you're dealing with both salt, sodium chloride, and water retention. They're both going to increase to counteract what those macula densa cells originally detected, the low flow of fluid or the low amounts of salt. All right. With that out of the way, we have to look into the filtration membrane itself, though, because that was occurring based on what's in the filtrate, but how do we get there? The initial filtration membrane, fenestrated endothelium. Fenestrated means you have more openings, more slits. That increases the amount of components that can fit through. You're also having the visceral membrane is found on the glomerular capsule, and a gel-like basement membrane. So a couple different layers here. But the overall goal is to control what's passing through. You don't want huge, large things like blood cells passing through. That would cause problems. So here are those filtration slits. You can see this right here is what we're looking at on the side, blown up more. So what you're actually seeing is each one of those little slits, each one of those little pieces over here, these slits, are going to be all of the fenestration slits. Their purpose is to control what passes through, so from the capillary out into the glomerular capsule. But the actual pores themselves down here, you can see the fenestrations. There's more openings. So it allows for more filtration to occur than a standard capillary that doesn't have fenestrations. So we're allowing water, we're allowing solutes, and most of them are smaller than the plasma proteins. You really don't want a lot of plasma proteins leaving. Those plasma proteins need to stay in the plasma, hence the term plasma proteins. So the fenestration slits are helping with keeping that there, as well as keeping the blood cells in place. So anything that's larger stays in the blood. That's not how you're filtering out. Your kidney is meant for small filtration. Looking at ions, chemicals, small chunks of broken down cell debris, but not full plasma proteins, not full cells like your red blood cells, your white blood cells. Those stay in the blood. And to help out with that, the negatively charged basement membrane is going to repel larger anions. So it kind of helps steer them away, so they're not even trying to push their way through. So you're utilizing both a physical barrier by size and a charge basis here to help keep them away. So a little about how the filtration is working, as well as some of the chemical receptors in the juxtaglomerular apparatus and macula densa.